Okay, welcome Frosh. Like you guys voted for, this is going to be the first video going over some midterm review stuff for you. If you aren't one of my kids, I'm Jack. I'm TAing this course. I made a little website. I'm basically just going off of stuff that's on my midterm information tab, some past examples from problems I think will probably be useful for you. Just a disclaimer, haven't seen the midterm. Please don't copyright me. I'm just trying to help you guys explain like you guys voted for. But yeah, okay, we're just gonna dive right into things. So obviously, this is your linear algebra midterm. Linear algebra is all about the study of essentially lines, or at least linear vector spaces. Now, a vector space is just like a rigorous redefining of math. It's probably pretty familiar to you. It has the operations addition or at least vector addition and scalar multiplication. The axioms, there's 8 axioms. They essentially just work how you expect math to work. I don't think you need to be concerned with memorizing, the commutativity of addition. You can simply just like swap elements if you need to. But yeah, just more rigorous definition of space. It's pretty useful for a lot of applications like machine learning. But yeah, it's pretty useful. We're just gonna dive into some of the basics here. So these are a bunch of definitions you should probably know, and then a bit about how you can actually go about applying them. So this first question from 2022, I guess question 4 actually, asks us to define what it means for a set of vectors of v1 to vn in a vector space V to be linearly dependent. Now to first motivate this, I think we need to talk about independence. So linear independence is this idea where when you add and scale your vectors by some scalar alpha, and you have that equal to 0, then the only possible solution is this trivial solution here, where alpha 1 all the way up to alpha n, every single one of your scalars is 0. So essentially, you can't add these and scale them to be each other. You need to send them all to 0, and that's the only way to get 0. To think about this a bit further, let's say you have this case over here where you have the x-axis and the y-axis are more, 1, 0, and 0, 1. I think we can agree that's like I hat and j hat. So there is no way to multiply I hat to get to j hat, right? There's no alpha times 1, 0 that's going to equal beta times 0, 1 that isn't just this trivial solution of alpha and beta both being 0. So that's kind of the notion of independence. You can't construct a vector simply by adding and scaling the other vectors in your set. Now, to rigorously define independence, we're going to use some math notation here. So this means there exists a scalar alpha I, which is a real number, and I is just an index, which is between 1 and n, corresponding to our 1 and n, or 1 through n vectors here. And these alphas are going to satisfy an equation, which is alpha 1 times v1 plus alpha 2 times v2, added all the way up to alpha n times vn is equal to 0. Essentially, if we can find one single alpha that's non-zero, just 1 is fine. Generally, it'll be more. Just 1 is fine. If you can find one of these alphas that's non-zero, that means you have some notion of dependence. Now, a better way of thinking about this is that if you have a dependent set of vectors, let's call this set dependent, and we're just going to choose an arbitrary vector in it. If you have this notion of dependence, then any vector in that set can simply be described by adding and scaling the other vectors in your set, okay? So if we call this back to our R2 example, if we're trying to look at 3, 2, 3, 2 would be linearly dependent if it was in a set with I hat and j hat over here, right? Because as you'll see later, these I hat and j hats form a basis of R2, meaning that they're like the least information that you can describe anything in R2 from. So this 3, 2 is simply 3 times I hat plus 2 times j hat. And that's obviously going to get you to 3, 2, right? So that set would be dependent because you can construct it from any of the other ones. But this works both ways because, if 3 times 1, 0 plus 2 times 0, 1 is equal to our vector 3, 2 over here, that means we can also just like move these things around and construct any of them by a linear combination of the other ones. Okay, so diving into our next definition here, the span is essentially all possible linear combinations of your set of vectors. In rigorous mathematical terms, we have if vector is an element of our span of the vectors v1 to vn, that is the same thing or equivalent, also known as if and only if you see it in a proof, that means that vector can be constructed as a linear combination of the others, or as adding and scaling your other vectors. V is equal to alpha 1 times v1, added all the way up to alpha n times vn. So that's what it means for a vector to be in a span of something. Next, we're going to talk about like your first little proof question. This is not that rigorous, but you need to start every proof with an assumption. So here we have the case where we have the zero vector and we have an arbitrary non-zero vector in our space. We want to know if this set of the zero vector and v are linearly independent or dependent. So we're going to start with assuming that we have two scalars, alpha and beta, that are real numbers. And we're kind of just going back to this golden equation here of what happens when we add and scale them and set it equal to 0. So if we take alpha times the zero vector plus beta times our other vector, that's kind of just the exact same thing by moving alpha times the zero vector to the other side as beta times our vector being equal to negative alpha times our zero vector. Now, since like zero is zero. It works how you expect zero to act. When you multiply anything by it, you should also be getting that same zero vector back, right? So that means we can choose any alpha. 0 would work, but alpha equals 3 would still result in a right-hand side of the zero vector. And that matters because there's nothing else this right-hand side can equal. So we've already kind of found a scalar that isn't 0, which breaks our notion of independence. So we already know this has to be dependent. But defining this a little further, if we chose beta is 0, which we have to do by necessity, and any alpha, let's call it alpha is 3, then we're going to have a non-zero scalar solution to this golden equation. Now to define the zero vector a bit more, it's generally your familiar notion. So for example, the zero vector that's in R3 is 0, 0, 0, at least under normal vector operations, okay? But really the zero vector is this kind of identity element where, like you would expect, you add 0 to any vector or anything, and you're going to get back that same thing or vector. Generally, you also have the same thing where if you multiply the scalar 0 times any vector, you're going to get the 0 vector back. Now, this is always true, but if you have a weird vector space where you have multiplication is exponentiation, for example, this notion of applying 0 times a vector might not necessarily be true. But otherwise, you can use either of those properties to find the zero vector, can be pretty useful. And it's really important. Essentially, the zero vector, we'll talk about this when we do a subspace question, but the zero vector is foundational to most of the axioms. So you need the zero vector in your space, which isn't really a shock. 0 is pretty core to a lot of how you do math. Okay, we're going to move on to the last question here, which is pretty easy. So we have a set of vectors, v1 to vn, and then we have some other vector v that's within the span of these. Now, recalling up here, the span is a linear combination of those other vectors, right? It's some scalar times our vectors added together. So if we have a vector in our span, we know it can be written as a linear combination of, our vectors v1 to vn. And this means for we have some real scalar multiples. And that means that v can be constructed solely by multiplying those scalar alphas times our vectors. So I guess in the arbitrary case, if we have the zero vector, this works out. You can, alphas can be anything. Or if you have the zero vector, I don't know. That's a weird case. We're not going to talk about that. If you don't have the zero vector that you're kind of trying to construct, essentially, that means that you have to have some alphas that are non-zero, and that, obviously, as we talked about before, means that our set would be not independent, or we'd have a dependent set, which kind of makes sense. So if you have a set of vectors, let's say they're independent, And then we have another vector that's equal to adding and summing these, or scaling and adding these vectors, then it makes sense that we no longer have that notion of dependence, because now we have some element that we can move stuff around for, and it can be constructed by all the other stuff. So if we want to describe V1, for example, we could have, 0, or we could have something like V1 is equal to alpha 2 over negative alpha 1 plus all the way, this is times V2, plus all the way to like the same alpha n over negative alpha 1 Vn. So we can move anything around, and we can construct any vector from any other set if it's within our span. That kind of wraps it up for the basics for right now. I've left 2 other questions as exercises here, just as a little review for what's to come. I obviously have our 2 tutorials are next week on Thursday and Friday, but I'll also be teaching the EngLinks workshop for this class on Saturday. I think it's 2 to 4 in Sterling. And then I'm also doing a help desk from 6 to 9 in the ILC on Monday, the day before your midterm. Like I have up here, your midterm is on February the 11th. I think it's next Tuesday. But yeah, this is the first video. We're going to go over a couple more. Good luck, though.